In the previous video, I showed you the physical and historical context as well as the motivations of this Stern-Gerlach experiment. Now, I want to explain why their results are correct, but for the wrong reasons. This is a follow-up video on the Stern-Gerlach experiment, so make sure to check that video for context. I would like to emphasize how lucky Stern and Gerlach were that they got the correct result at all. In addition to all the issues that plagued the experiment, from plane crashes to hyperinflation, there were a series of lucky mathematical cancellations as well as fortunate coincidences that led to their success. I told you about the bad cigars that helped Stern and Gerlach to see the silver atoms collected by their detector, and the millionaire banker that donated funds to save the experiment. But there were more instances of good fortune. The day of the successful result, February 8, 1922, Gerlach sent Otto Stern a telegram simply saying, "Bohr is right after all." He also sent him a letter with details and copies of the now historic photograph. The experiment finally worked and confirmed the split of the atomic beam in two equal parts, as predicted by the quantum theory of Bohr, Sommerfeld and Debye. Gerlach also sent a postcard to Niels Bohr with a copy of the microphotograph of the split beam and the following message: "Attached is the experimental proof of directional quantization. We congratulate you on the confirmation of your theory." This celebration was quite premature because Bohr's prediction was correct, but for the wrong reason. In fact, other things that Stern and Gerlach concluded were also right for the wrong reason. I insisted at the beginning of the previous video that our modern interpretation of the Stern-Gerlach experiment is that the beam splitting was a consequence of the electron's spin, but that is not what Stern and Gerlach reported and what the physics community celebrated. Just to be clear, the splitting observed by Stern and Gerlach was produced by the spin of the electron and not by the quantized orbital angular momentum, or space quantization as they called it back then. Quantized orbital angular momentum is a real phenomenon, but this was not observable in the experiment set up by Stern and Gerlach. This involves two coincidences. The first coincidence was the choice of silver for the atomic beam. Silver is chemically stable and easy to evaporate in the oven of the experiment, which made it a great choice. This is a representation of a neutral silver atom with its 47 electrons. You will immediately notice that one electron is alone in the fifth level. Another way to see this is by filling orbitals using the rules that you might recall from your chemistry class. This is the electronic configuration of silver, where again we see the ampere last electron in the fifth level, with zero angular momentum. It turns out that the orbital angular momentum of the atom is zero, which according to the Bohr-Sommerfeld-Debye theory leads to a zero orbital magnetic moment, and therefore zero force even in the presence of the non-uniform magnetic field. In other words, Stern and Gerlach didn't know it, but according to the theory, the beam should not split at all. But another thing that they didn't know back then was that the ampere electron has an angular momentum that has nothing to do with its motion. It is an intrinsic angular momentum, quantified by a new quantum number, ms, called spin. The accidental combination of these two effects led to the beam splitting observed in the experiment, which revealed the spin of the electron, although Stern and Gerlach incorrectly interpreted as the confirmation of the Bohr-Sommerfeld-Debye theory. I will discuss spin in more detail in a future video, but for now we can understand the result of the Stern-Gerlach experiment as a consequence of a fourth quantum number that can take two values, +1/2 or -1/2. Being an intrinsic angular momentum of the electron, this new property produces a magnetic moment given by this. This relation is analogous to the formula derived by Pauli that I showed you in the previous video following a classical electron orbiting the nucleus. I will get back to this expression in a minute. In summary, the ampere electron and its intrinsic angular momentum, that we now call the spin, is what made half of the silver atoms in the atomic beam go up and the other half go down in the Stern-Gerlach apparatus. But again, they didn't know about this and incorrectly attributed the splitting of the beam to space quantization. In a long article published during 1924, Stern-Gerlach described more details of the experiment and concluded with this. The tests described above provide the experimental proof of the Debye-Sommerfeld magnetic directional quantization and the experimental determination of the Bohr magneton. I hope it is clear now that statement number 1 is wrong. Stern-Gerlach discovered a crucial quantum effect that confirmed Bohr's prediction, but it was not caused by directional quantization. It was the consequence of the unintended combination of using silver for the atomic beam and the spin of the electron. A second coincidence has to do with statement number 2, which is correct due to a lucky simplification of terms. The splitting of the beam is a qualitative feature predicted as a possible outcome by Stern in his original design of the experiment that he published in August of 1921. But he also provided a way to verify Pauli's prediction of the magnitude of the magnetic moment, which Pauli called Bohr's magneton. The idea is as follows. Looking at the experiment from a side view, a silver atom of mass m moves with a constant speed v before entering the non-uniform magnetic field. Inside the magnetic field region of length L, the atom is accelerated along the z direction. Up or down, the effect is symmetric. Let's call delta z the magnitude of the vertical deflection of each atom with respect to the original beam. Using simple kinematics, this vertical deflection is given by 1/2 a delta t squared, where a is the vertical acceleration given by the ratio between force and mass, and delta t is the time that the atom spends in the magnetic field region. This time can be obtained from the motion along the horizontal direction, where the speed is constant, so that delta t is the horizontal length of the magnet L divided by the speed v. Putting all this together, we find that the deflection is given by this expression. We still need to determine the speed of the atom in the beam, for which Stern related the average kinetic and thermal energy of an atom in the oven at temperature T in this way. By the way, this is exactly what we did in the video about the Frank-Hertz experiment. Using this relation, the deflection becomes this, which is what Stern originally proposed in his paper. In the experiment, Stern-Gerlach measured the temperature of the oven, the magnetic field gradient, the length of the magnet, and the deflection delta z. They also evaluated careful deviations from this idealized relation, but in the end what they did was a comparison between the measured deflection and the calculation, assuming that the atom has a magnetic moment equal to 1 Bohr magneton, as predicted by Pauli, and the agreement is remarkable. Several viewers have shared that sometimes they cannot follow all the math and calculations, like the one we just did, but they still enjoy the content. In today's video, we use results from kinematics, dynamics, and conservation of energy, topics that I encourage everyone to learn in a fun way thanks to the sponsor of this video, Brilliant. With thousands of interactive lessons in physics, math, data analysis, programming, and AI, Brilliant is where you learn by doing. Whether you want to build problem-solving skills or develop a powerful daily learning habit, Brilliant has a lesson for you. If you want to follow all the steps that Stern proposed to measure Bohr's magneton that I show you above, I highly recommend the course Classical Mechanics. It covers all the necessary topics from the equations of kinematics and energy conservation to forces and laws of motion, and more. And you can try it for free for a full 30 days. Visit brilliant.org/jk0 or scan the QR code on screen. You can also use the link in the description. For viewers of this channel, Brilliant offers a 20% off an annual premium subscription. Thank you for supporting the channel using my link, and thanks to Brilliant for sponsoring this video. From the remarkable agreement between the calculated and observed deflection, Stern-Gerlach concluded what they reported as statement number 2. The magnetic moment is exactly 1 Bohr's magneton. But since we know today that Stern-Gerlach measured the effect of spin rather than space quantization, you may wonder, how is it that they found exactly what Pauli predicted? The answer is a coincidence in the formula for the magnetic moment. In the previous video, I show you how Pauli found this relation for the magnetic moment produced by orbital angular momentum, which is what Stern-Gerlach used. But in reality, the magnetic moment was produced by the spin of the electron, in which case they should have used the formula shown earlier, where ms is plus or minus 1/2, and gs is the so-called spin g factor of the electron. Gs has been measured and happens to be around 2. Here we see that the combination gs divided by 2 is very close to 1, in a coincidence that some authors call a natural conspiracy, because it fooled Stern, Gerlach, Bohr, and almost everyone else by hiding the true effect of the electron's spin and making it look like space quantization was the cause of what was measured. This coincidence is the reason for Stern and Gerlach correctly measuring Bohr's magneton, despite the fact that the deflection was produced by spin. Notice that I said that this coincidence fooled almost everyone. There were 2 German theorists that predicted a new quantum number. Both were students of Sommerfeld. Alfred Landé graduated from Sommerfeld's group before the war, and when the Stern-Gerlach result was published, he decoded its meaning in the correct way immediately. Landé was studying the so-called anomalous Zeeman effect in July 1921, when he introduced the concept of the G factor used above, as well as an extra quantum number that he called MR, and could take the values plus or minus 1/2, very similar in form to what today we call ms for the spin. In what we could call an unfortunate coincidence, Landé was a physicist in Frankfurt at the time of the Stern-Gerlach experiment. He was literally sitting in the building next door, but his ideas were ignored by the theory community for years. Stern and Gerlach didn't know about Landé's proposal at all. Landé published an article explaining the splitting in the Stern-Gerlach experiment, but he did not provide explanations for the new quantum number, or the G value. It was mostly a semi-empirical description rather than a well-founded theory. And Landé was not alone. During 1922, another of Sommerfeld's students in Munich proposed the possibility of a half-integer angular momentum. Sommerfeld hated the idea, but he encouraged his young student to publish his article. Years later, this student, named Werner Heisenberg, will realize that the Stern-Gerlach apparatus was crucial for one of the most fundamental ideas in quantum mechanics, the uncertainty principle. Einstein, as a promoter of the experiment as well as a financial supporter, was the first to address the results in a scientific publication. Together with his close friend Paul Ehrenfest, they tried to explain the perfectly symmetric splitting of the beam in terms of classical electromagnetism and thermodynamics. They analyzed all the possible effects that could make the randomly oriented atoms align in the magnetic field. In August of 1922, Einstein and Ehrenfest found that classical processes could in theory align the atoms as observed, but it would require a magnet almost 40 times the distance from the Earth to the Sun. Since the magnet used by Stern and Gerlach was only a few centimeters long, the conclusion was that classical physics just could not explain the perfect beam splitting. The next action by Einstein was immediately nominate Stern and Gerlach for the Nobel Prize in Physics. Interestingly, this groundbreaking experiment was never recognized by the Nobel Committee. After receiving 82 nominations, Stern finally received the Nobel Prize 2 decades later, but for other remarkable measurements that he did in Hamburg, and not for his experiment with Gerlach. There is no official statement on why Gerlach, nominated 30 times, was not awarded the Nobel Prize. The unofficial story is that the Nobel Committee left Gerlach out due to his involvement with the German nuclear program during World War II. In fact, if you watched my video about Heisenberg and the German bomb, you will remember that Gerlach was one of the 10 prisoners of Operation Epsilon. In the previous video, I left some details out that led to many questions in the comments. I want to address the 5 most recurring questions that I received. By the way, thanks so much for these great questions. I am delighted to see that the videos not only serve as a way to share the story of crucial experiments in physics, but also actively engage viewers, making them reflect and challenge the content, triggering these high-level questions. Please keep them coming. What went wrong in late 1921? Why was the beam splitting not observed then? This is a really good point. I described that in late 1921, Stern and Gerlach managed to run the experiment and obtain only an inconclusive result. The main issue was collecting enough atoms on the glass plate to make them visible. Running the experiment for many hours without something breaking was a great challenge. They ran the silver oven at 1000 degrees, which affected many of the components inside the vacuum chamber. Rubber O-rings melted all the time, preventing the vacuum pumps from operating properly. If you have ever worked with low-pressure equipment, you know that a faulty O-ring can cost you weeks or even months of work. I will never forget my first assignment when I joined a plasma physics lab more than 20 years ago, finding a leak. Those O-rings are great when they work, but they can be a nightmare when they don't. This is why Gerlach spent the night of February 7th, 1922, babysitting the experiment. Nothing broke for hours, so he kept it running. In the early run of the experiment during 1921, they did observe a weak widening of the beam, which could have been incorrectly interpreted as a confirmation of the classical result. But this could also be caused by the 3 lines predicted by Sommerfeld being superimposed. In the end, they needed more data, better beam alignment, and hopefully a narrower beam, which is related to the next question. What did Gerlach do different after Stern left? Gerlach kept fixing the apparatus and improved several components, but there was one significant change to the experiment that took place in early 1922. A small conference took place in Göttingen, which Stern and Gerlach attended. A common practice between scientists collaborating at a distance is attending conferences to meet in person and make progress. Stern and Gerlach used the meeting to review the state of the experiment, and after months of unsuccessful work, they were ready to give up. Fortunately, luck struck again. After the conference was over, Gerlach could not return to Frankfurt due to a railroad strike. They used the extra day to review all the details of the experiment one last time. Up to that moment, the collimation of the beam used a circular hole followed by a rectangular slit. During the day that Gerlach was trapped in Göttingen, they agreed that maybe this circular hole was causing an artificial widening of the beam and decided to give it a try one more time, but using 2 rectangular slits instead. This would make the beam narrower and sharper, which would allow them to distinguish between the beam widening or splitting. This last modification proved to be the right thing to do. After this modification, Gerlach achieved a perfect beam alignment, leading to the successful result of the night of February 7th. Has this experiment been reproduced? Yes, of course. Stern and Gerlach themselves repeated the experiment many times. Later, they independently repeated the experiment even with different atoms. And of course, this experiment was quickly reproduced all over the world. But don't take my word for it. There is a fantastic 1967 video by the MIT Physics Instructional Resources Lab, where they show in detail a reproduction of the Stern-Gerlach experiment using cesium atoms.
Perhaps you already know that magnetic atoms can't just have any orientation in a magnetic field, an effect that can only be explained by quantum theory. An experiment similar to the one you see here was first done in 1922 by Professor Otto Stern and Walter Gerlach.
Link is in the description below so you can check it out later. Between 1927 and 1828, Einstein and Heisenberg proposed the idea of 2 and even 3 sequential Stern-Gerlach experiments with their magnetic fields in different directions. These so-called multi-stage Stern-Gerlach experiments are the basis for modern introductions to quantum mechanics and quantum computing. It took a few years, but they were finally carried out during the early 1930s, among others, by Stern and his students Otto Frisch and Emilio Segre. These and other modifications of the original Stern-Gerlach experiment would later lead to the discovery of nuclear magnetic resonance, the physical principle behind every MRI machine used in hospitals around the world. This work was pioneered by Isidor Rabi, who was trained by Stern in Hamburg during the late 1920s. Rabi received the Nobel Prize for his work a year after Stern. As a side note, if you watch my series on the physics of nuclear weapons, some of these names might sound familiar. Otto Frisch, with his aunt Lise Meitner, explained nuclear fission, and then with Rudolf Peierls, another of Sommerfeld's students, were the first to calculate the critical mass for an atomic bomb. Emilio Segre was one of the discoverers of plutonium, and Isidor Rabi worked closely with Oppenheimer and even made it to Christopher Nolan's film. Back to the multi-stage Stern-Gerlach experiments, Einstein and Heisenberg began questioning how and where the atoms in the beam decide to move up or down. They were beginning to ponder one of the most disturbing aspects of quantum mechanics that even today doesn't have a solution: the measurement problem.